Hello? Hello? Hi guys, good afternoon. I would say this is good evening. I see almost, good evening. So I see almost, I don't know, some 10 or so people. So we will wait for 2 more minutes. Let your friends join.
Sir,
Yeah.
I'm a new student. My name is Nanda Kishore.
What is your name? Ananda Kishore. Okay, Nanda Kishore. Please tell me. Yes.
Oh.
Yeah. So this is your first class for chemistry,
Yes.
Nanda? Okay.
Yes.
Okay. So we have completed one chapter. I'm taking the physical chemistry part and maybe some inorganic, and the other faculty for chemistry will be taking the organic part. So what to say, the recordings would be available with you. They would have given you the recordings, isn't it?
Yes, sir.
Did they give you? Yeah. So please go through it. If at all you have any doubts regarding any of the chapters, you can always contact me. Right? Your friends will have do you know anybody from the class?
No.
From the existing students? You don't know anybody? Okay.
No.
So maybe at the end of the class, I'll give you my number. You
Okay.
can always contact me if you have any doubts.
Okay.
Is it okay, Kanna? Right?
Yes.
Cool.
Thank you.
Yeah. Right. So I see most of you are there. Right. I think it's a good time to start. I don't know whether I'm made the host. Yes, I am the host. Okay. Fine. So guys, let me share my screen and then we'll start.
Which chapter?
These were your papers which I corrected. Hope you all got your papers. Was there any problem, guys? In the correction, you want to know anything regarding the correction, the answers, anything? Any queries?
I didn't get my paper.
Is it Mithun?
I didn't get my paper.
Nobody got the papers?
No, sir.
I checked it.
Oh. Okay. But I have given the papers to the management. Maybe you'll be getting it very soon. Right. If at all you want to know your marks, you want to know your marks? Guys?
No, send it.
It's fine.
Okay, sir. Sure, sir.
Okay. What? Okay, fine. So anyways, if you don't want to, where is my, I want to have to increase the volume. Yeah, now it's fine. Cool. So guys, we'll start. Okay. If at all anybody is interested in knowing their marks, you can always text me personally. I can give you your marks. Right? Okay, cool. So maybe this is 12 and today's date is 11. This is 6th month, so 06, right? Okay. So yeah, so last class we didn't do much, as we all remember, right? So we were just revising what we were seeing, what we have seen with respect to solutions chapter. Only a small part is left, so that will quickly revise and we'll do some couple of problems and we'll move on to electrochemistry. So I have decided that the next chapter would be electrochemistry. Okay, I hope everybody is cool with it, right? Okay, fine. So the thing for today is this abnormal molar mass, right? Now, fine. So we already mentioned that the main application of colligative properties, we know that we have 4 colligative properties. You know all these 4, and say, where are these colligative properties used? Why are you even studying them? Anybody wants to answer? Why are you even studying them? What is the application point of view for colligative properties?
Find the mass of a substance, this all.
So yeah. Okay. Anybody wants to give a little more, answer with more clarity? That's correct what you said.
So to find the unknown mass of a substance without taking into consideration of its nature, independence of its nature.
Okay, fine. I'm getting a little more closer. So basically, what we are trying to do is say I have a solution with me. Okay. Now this solution, say I know the solvent, for example, I know solvent is water. Okay. Now I have mixed some unknown solute to it. Okay. So even though I don't know what is the solute I added, obviously if I know the solute, I know the molecular formula, I will know what is the molecular mass. That is very easy. But if I give you a solution where you know the solvent, say solvent is water, but you don't know what is the solute, right? With the help of colligative properties, you will be able to, find the unknown molecular mass, not the structure, not the formula, nothing, but we'll be able to find the molecular mass. Okay, fine. So that is the main application of colligative properties. And for determining the molecular masses, out of the 4 colligative properties, which one is the best one?
Osmosis, sir.
Osmotic pressure. Why? Then I
The
gave you 2
value we
reasons.
get will be high, sir, so it's easier to calculate
Yes.
from that.
Yes, that is one definite reason. Say if I go for say depression and freezing point, or say elevation and boiling point, the value, the delta TF, delta TB values which we get is very small, like say 0.01, 0.03, something like that, very small values to work with. Right? But you can see in your problems as well, if you have solved for osmotic pressure, you will see that the value will be a considerably higher value. So calculation will be a little easy. Okay, what is the next point?
The other colligative property is the temperature should be increased.
Correct. So basically the osmotic pressure experiments can be done at room temperature, right? Even at normal room temperature, 25 degrees Celsius, I'll be able to do the calculations or do the experiment. But for say elevation, boiling point, or depression and freezing point, you obviously know that I have to, increase the temperature or say decrease the temperature. Okay, fine. So these are all the things, right? Okay, now moving on, what do you mean there is abnormal molar mass, or say we are going to have some problems, right? So like as we all know how the colligative properties are defined, isn't it? The colligative properties are properties which are independent of the nature, but just depend on the amount of substance, correct? So say for example, if I'm going to have a compound which is capable of undergoing dissociation, say ionic compounds, right? Or say some compounds capable of undergoing association, right? So at that time, the colligative properties will not be able to understand that this is the same compound that's undergoing the dissociation or association. So it will treat, say, for example, if it is say NaCl becoming Na plus Cl minus. Now we understand obviously that NaCl is a single compound, right? But what colligative property will take, for example, say if I tell you that 1 mole of NaCl is present, so obviously I will have 1 mole of this and 1 mole of this, right? So if now forget about the what is the nature of the compound and stuff. Now if the colligative property looks at it, how it will look is, now we know that there is only 1 mole of NaCl, right? But what colligative property will think is that I'm going to have 2 moles of the compound, that is 1 mole of Na plus and 2 moles of Cl minus. So that is where the problem comes. Okay, that is where the problem arises. So obviously through the calculations, if you're going to find the molecular mass, and that's what we're trying to do, right? So because of this problem, I'm mentioning that say 1 mole of NaCl gives 1 mole of Na plus and Cl minus, considering it as 2 moles, obviously the molecular mass which you're going to obtain is going to be wrong. Okay, right? So, and this the same thing happens with the association also. Say if I have 2 moles of BH3 forming B2H6, right? So again, I understand that there is say 1 mole of this, and obviously I will have 0.5 moles of this. So instead of the value we should consider, the colligative property should consider is 1 mole, right? But what it will consider is going to be 0.5. So again, there'll be a mismatch, right? So to overcome all these problems, we have what is called as your Bantoff factor, right? So we'll just move on. So there is this thing called as Bantoff factor, right? Yeah, right. Bantoff factor. It is denoted by the letter I, right? So now we know how to define them, right? So I'll be able to define them in 3 ways, guys, right? First way is by giving the first formula I is equal to the expected, okay, I would say okay, fine, observed molecular mass divided by the calculated molecular mass. right? Calculated molecular mass means calculation from the colligative properties, right? If I give you all the values, right? Say, for example, if I take for NaCl, right? We know the observed. Oh wait, it should be opposite. I'm sorry, guys. This is exactly opposite. This is ulta, right? Actually, this should come here, and this should come down on the denominator. I'm really sorry. Please change it. Okay. So it is basically calculated molecular mass divided by the observed molecular mass. Okay. Now, if you calculate the molecular mass of NaCl through the colligative property, you will find that the molecular mass which you obtain would be around 118, something like that. Okay. But we know what is the absolute molecular, well, we know what is the observed molecular mass, or we know what is the actual molecular mass of the compound, that is 58.5, right? So approximately, I can tell that the Van 't Hoff factor you will be getting is 2. Okay, right? So this is what is Van 't Hoff factor in terms of molecular masses, right? Now, same thing can be defined in terms of the colligative property value also, right? So that would be I, all right, okay, I is equal to the observed colligative property divided by the calculated colligative property. Okay, now what do you mean by this? Say, for example, I take any colligative property for the matter. Say I take delta TF is equal to KF into M. Right now, this delta TF you see is measured. You can see it's easily measurable. With the help of thermometer, you'll be able to measure it. And this is what I have to put it here. In the sense, the observed, what we observe with the help of the thermometer, what we actually see. Right now, calculation is this. Obviously, you calculate the colligative property through the multiplication of KF into the molarity. Right, that will come in the denominator. Okay, fine. So why are we doing all this? Because we said that there are going to be mismatches with your what is that? The calculation of molecular masses. So to correct this, what we do is I'm going to use this Van 't Hoff factor, right? So you are going to include this Van 't Hoff. Say, for example, like you can actually find the correlation here itself. Now, if I bring this here, I can write I into the calculated colligative property. I into the colligated property will be equal to the observed colligative property. So you can easily see if I can just include this I here, delta TF is equal to I into KF into M, the calculated and the observed will be matching. Okay, right. Now, this can be done for all the colligative properties. Say, for I think I've already mentioned it, say delta TP and delta TF will be same. Delta TP will be equal to I into KB into M. Say I can write pi is equal to I into C into R into T. Same way I can write del P divided by, say, PA naught will be equal to I into X. So you see, I'm including this I value for all the colligative properties. Okay, now for which compounds you should use I, which compounds you should not use I, they will not be mentioning in the questions. Please remember this. Okay, they'll not be mentioning in the questions. Now, from the compound mentioned, right? What type of compound mentioned, you have to understand whether I have to use I or not. Okay, say for example, they give you glucose. C2H6, C12H6, whatever it is, C6H12O6. Yeah. So if they give you glucose, I know glucose is not capable of undergoing dissociation nor undergoing association. So for those kind of compounds, I don't need to use I, right? But if they give you anything like, say, an electrolyte is present, right? We'll see what is an electrolyte when you go for electrochemistry. Anyways, so when they give you electrolyte is something which can produce ions, as simple as that. Okay, so if they give you anything with respect to an electrolyte, or they give you any salt, which you know, obviously, which they will undergo dissociation, at those times, definitely you have to use the I value. Okay, right. Now we saw two definitions, one with respect to the molecular mass, the other with respect to the colligative property. Now, third way is the most useful way for doing problems, I would suggest, is by using this. Now, I'll be able to define it as total number of moles at equilibrium. I think we've already seen this, just giving you a quick recap. Now, what do you mean by total number of moles at equilibrium? Like, I'll just take one example, maybe a good example. Say I take MgCl2 giving Mg2 plus Cl minus. Okay, right. Say now I start with 1 mole. We always start only with 1 mole, guys. It is assumed that we always start with 1 mole. So 1 mole of this initially, I will not have any dissociation start. Assume that at time t is equal to 0. This is at time t is equal to 0 when nothing has started. Right now at equilibrium, right? At equilibrium, what would have happened? Say now we go into the equilibrium chapter which you saw in your 11th class. So I take alpha as the degree of dissociation, right? So hope you remember alpha. Alpha is degree of dissociation, which tells you out of 1 mole, right? Out of 1 mole of the compound, how much is undergoing dissociation, right? How much is undergoing dissociation. So I write now, obviously some alpha moles would have reacted, right? So now you can see 1 mole of this gives 1 mole of Mg2 plus and 1 mole. Oh, I should write on the, sorry, there should be a 2 here, right? Because there are 2 moles of Cl minus. Okay, fine. So 1 mole of MgCl2 will give 1 mole of Mg2 plus and 2 moles of Cl minus, right? So if alpha moles of MgCl2 are reacting, I will get alpha moles of Mg2 plus and how many moles of Cl minus? 2 alpha. Right now, what I have to do, I have to see what is this. I have mentioned it here. I is total number of moles at equilibrium. Now you see there are reactants, there are products. Now I have to take a total of all these 3. So I'll be getting 1, say 1 minus alpha plus 2 alpha. So I can write I, which is equal to total number of moles at equilibrium, to be equal to, can I write it as 1 plus 2 alpha, right? 1 minus alpha plus alpha gets cancelled plus 2 alpha. So it will become 1 plus 2 alpha, right? So what you understand from here is the I value, right, will depend on the degree of dissociation, not only for this compound, for any compound for that matter, right? The I value will be dependent on the degree of dissociation or the association for that matter. We'll see maybe an example for association also, right? Okay. So depending on the question, they might give you alpha, they might give you I and ask you to find alpha. So I think you must have solved at least 1 or 2 questions in your test regarding this. And most of you have done well. I'm seeing it. Most of you have understood whatever the concept you have been seeing. Okay. So this is what it is. Okay. Now, this is in the case of dissociation. Say what happens if I have association, we'll see, right? Association, say I take the example of B2BH3 to form B2H6. Say I have, so I have 2 moles of BH3 giving, not 2 moles, it's 1. Right, so it is going to give B2H6, right? So again, at time t is equal to 0, I start with 1, initially 0. At equilibrium, if you want, you can write at equilibrium, say I write 1 minus alpha. Now what should I be getting here for B2H6?
Is it
With
alpha?
alpha, yeah.
Alpha by 2, sir.
Alpha?
Alpha by 2.
It should be correct. It's alpha by 2. You can understand, guys, how is it? Say now you see there is 2 moles of BH3 giving 1 mole of B2H6, right? So if alpha moles are reacting, alpha by 2 moles of B2H6 will be formed. So if at all you want to avoid the confusion, you can write 1 minus 2 alpha here and alpha here. That is also correct. Okay, right? This you can write 1 minus alpha and alpha by 2, or you can write 1 minus 2 alpha and alpha. Both, or either way, you can understand that for one mole of B2H6, 0.5 moles of for 1 mole of BH3, 0.5 moles of B2H6 is formed. Like that is the correlation. Again, the same thing. The definition of I holds good. Again, it is equal to the total number of moles at equilibrium. So it will be 1 minus alpha plus alpha by 2, or you can write 1 minus 2 alpha plus alpha will become 1 minus alpha will be the value of I here. Right, again, in this case, alpha is the degree of association, not dissociation. This in this case is undergoing association. Right. So I think this is where the chapter ends. Maybe we'll just do quickly a couple of problems and then we'll move on. If you have any doubts, you can ask me, guys. Please go for it. Any questions?
Sir, when we calculate the Van factor, when we take degree of that's the equilibrium as 1 minus alpha and alpha by 2, we get another answer, sir. Like we are getting 1 minus alpha by 2. But if you take it as minus 2 alpha and alpha, we get 1 minus alpha, sir. So which one should we prefer?
1 minus alpha plus alpha by 2 will become 1 minus alpha by 2. And if I take 1 minus 2 alpha and alpha, I'm getting 1 minus alpha. Actually, how is it coming like this? It should be same, right?
2 minus 2 alpha.
Oh, correct. We should be actually taking 2 minus 2 alpha. But again, guys, you don't have to, maybe if you're getting confused with the second one, actually you can take this out. Not required. Yeah, I should be getting actually 2 minus 2 alpha. Correct. Anyways, don't confuse yourself, right? So if I write it properly, it will be 1 minus alpha plus alpha by 2 will become 1 minus alpha by 2. Right? 1 minus alpha by 2 will be the correct way of doing it. Okay, don't get confused. Okay, fine. So now maybe we'll do some problem. Quickly we'll do. Okay. Okay, let me see if you can solve this question. So they are telling there is a electrolyte. Okay, there is a electrolyte of the formula AXBY. Okay, there is a electrolyte of the formula AXBY. Right. So if I is the Van 't Hoff factor and alpha is the degree of dissociation, I want you to write alpha in terms of X, Y, and I. Go for it. Hope you understood the question. I have an electrolyte, right? I have an electrolyte AXBY. Its degree of dissociation is alpha. The values are not given, only the letters are given. Okay, these values are given basically. What is these? This X, Y, and I, we know, assume that. Okay, so what you have to do is write alpha in terms of X, Y, and I. That's what you have to do.
I have a doubt. Here X and Y are subscripts, right?
Yeah, it's like MgCl2. MgCl2, if I take X will be 1, Y will be 2, something like that.
Okay, sir.
Right? Yeah. It is just coming from the definition that I is equal to total number of moles at equilibrium. If you just make it, it's done. Please do not sit idle, guys. Everybody have a notebook, have a pen, start writing notes, start solving problems.
So I got alpha equal to 1 minus I by 1 plus X plus Y.
I think it should be correct.
I minus 1 by X, Y minus 1.
Okay, fine. So we'll check it out. I hope everybody has tried. We'll just check it out. So I'll just write the ionic equation first. AXBY will give X moles of AY plus Y moles of BX minus. I hope everybody understood how I wrote this equation, right? If you go back to your 9th class, people, right? You must have known how to write the formula of an ionic compound, right? For example, if I want to write, say, aluminium oxide, right? Aluminium oxide, if I have to write, I know aluminium forms Al3 plus, oxygen forms O2 minus. Now this will come here, this will come here, and that's how you get the formula as Al2O3, right? So what you understand is this 3, what I write is the valency for aluminium. And this 2, what I write is the valency for oxygen. And that's exactly what I wrote here. This Y right? This y, what I have here is the valency for A. That's why I wrote y plus. And this x, what I have here is the valency for B. That's why I wrote x minus. And the number of moles is same. This x moles of A and y moles of B. That is very easy, right? Okay. Now at time t is equal to 0, 1, 0, 0. Now I write 1 minus alpha. Here I'll be getting x alpha. Here I'll be getting y alpha. Now I think easily understood. 1 mole of this compound gives x moles of A and y moles of B. So 1 alpha moles will give x alpha moles of A and y alpha moles of B. That's it, right? So if I write my I value here, again, total number of moles at equilibrium, that will be 1 minus alpha plus x alpha plus y alpha, right? So I can write how? I can write it as, so it will be 1 plus x plus y minus 1 into alpha. There's a 1 here. Okay. So 1 plus x plus y the brackets x plus y minus 1 into alpha. Now that's it. I think you have to get the alpha. Maybe I'll write it here.
Doubt here.
Yeah. Tell me, Kana.
Wouldn't it be 1 plus x plus y into alpha?
1 plus
1 minus
what?
alpha into 1 plus x plus y.
No, basically it will be 1 minus alpha plus x alpha plus y alpha. So if I write it, it's correct.
You can
only,
take
right?
alpha common, right, sir?
Yeah, if I take alpha common, I'll get x plus y minus 1. For I have here the coefficient that is
Okay,
here.
sir.
The coefficient is 1, correct? So that's why I wrote x plus y minus 1. Yes?
Yes, I understood.
Okay. Yeah. So now if I write my alpha, so what will first happen? I have to bring this 1 to the side. So it will be what? It will be, it will be I minus 1 divided by x plus y minus 1. That would have been the answer. Yeah. Okay. I hope some of you would have gotten the answer. Very easy question. Just the definition. I didn't do anything extra from whatever I taught you. It's exactly the same. Okay. Right? I hope everybody understood. If there's any doubt, you can please ask me. Right? I didn't do just mathematical calculation. I just put I and alpha on either sides. And that's it. Right? So the answer is alpha is equal to I minus 1 divided by x plus y minus 1. That's it. Okay. Cool. Next question. Please take down the question, people. I'm going to dictate the question. Please take down the question. Right. 0.004 m, capital M, 0.004 capital M, Na2SO4 aqueous solution. Right? 0.004 capital M, Na2SO4 aqueous solution is isotonic with 0.01 capital M glucose solution, is isotonic with 0.01 m glucose solution at 300 Kelvin. At 300 Kelvin. Right. Now the question is, find alpha for Na2SO4. Find the alpha for, or degree of dissociation, if you want to write it big, you can write, find alpha for Na2SO4. I will repeat the question, people. 0.004 capital M Na2SO4 aqueous solution is isotonic with 0.01 m glucose solution at 300 Kelvin, not degrees, right? Find the degree of dissociation for Na2SO4. Okay, maybe I'll give you a minute, 2 minutes. Just talk out. How are you going to approach the problem? So we know what isotonic means, right? And they have given glucose and they have given Na2SO4. So yeah, you just have to connect all the points which you have ready, which you have studied. Please bear with it. Street vendors. There are so many chats which I didn't see. It says I have a doubt. Okay, I'll look into it. Alpha is 0.75. Maybe Satyapriya, your answer might be right. Sorry?
20% dissociation, sir.
Okay, that's what Satyapriya is also correct. We'll check. Okay, fine. I think the answer should be correct. It's 0.75 or you should write it as 75%. Both of it are right. Okay, fine. We'll check it. This background noise, even it's irritating for me, I can understand it'll be irritating for you, but sorry guys. Okay, right. So see, they're telling that I have Na2SO4 and glucose. Right. Guys, give me a moment. Just give me a moment. I'll just close the windows and come. Just give me a moment. Okay, right. So I know Na2SO4 will be able to undergo dissociation, and but glucose is not going to undergo dissociation. Right. Now they have given that. Oh, I hope I'm not on mute. Okay, fine. Right. So what I was telling, yes. So they're telling that these two solutions are isotonic, means I know that these two solutions are going to have same osmotic pressure. Right. That's what it means. Right. So if these two solutions are isotonic, they will have same pi value. Right. That means what? How can I write it? I can write pi of Na2SO4 will be equal to pi of glucose. This I'll be able to write. Right. And since it is Na2SO4, which is an ionic compound, how will I write the formula for this thing? It will be I into C into R into T. The concentration of Na2SO4 is 0.004 m. R into T, I'll keep it as R into T. Okay. Now here, which is equal to the pi of glucose, and glucose is not going to undergo any dissociation or association, so I don't have any I. So directly it is going to be pi into C. Pi is equal to C into R into T. And C here is how much? 0.01 R into T. So let me cancel RT because they are given the temperature as 300 Kelvin for both of them. So both RTs and the RT here is getting cancelled. So I can easily tell that the I value would be 0.01 divided by 0.004, or I can write it as say if I multiply above and below by 1000, what will I get? I will be getting 1000 means I'll be getting 10 divided by 4, which is 2.5. So what I'm seeing here is the I value is 2.5. Now this is not the answer, people. Right? This is not the answer. This is just the I value. With the help of I value, now I have to calculate what is the alpha value for Na2SO4. Now we'll try to do that. We have to go for the ionic equations. Right? So I write Na2SO4 will give Na 2 moles of Na plus SO4 2 minus. So if I start with 1 mole, 0, 0, and if I have alpha moles reacting, I'll be getting 2 alpha and alpha. Yes. Okay. So now I can write I is equal to, again, total number of moles at equilibrium. So it will be 1 minus alpha plus alpha will get cancelled. So I'll be getting 1 plus 2 alpha. And I know what is the alpha I value now. I value is 2.5, which is equal to 1 plus 2 alpha. So it will be 1.5 divided by 2. Yes, alpha value is 0.75. Okay. Like this, only questions will be asked. So you have to know for which compounds you have to use I and for which compounds you should not use I. Right? And you know, isotonic means I'm going to have same osmotic. So yes, tell me.
Sir, so only for ionic compounds we need to use I as a prefix, right?
Correct, correct. And for anything which they give you like BH3, that and all, if they give you, then you have to understand that I have to again use I. But in those cases, it will be association, like coming together. But again, those kind of questions, they'll not be asking you much. 99% they'll not ask you. But if they ask you any Van der factor question, it will be like ionic compounds undergoing dissociation. Right? Okay.
So in association, the 0.044, like the given M value will be greater than 1, no, sir, if they give association.
If they give association, I value will be lesser than 1.
Oh, okay, sir.
If it is dissociation, I value will be greater than 1. Okay, right. Fine. So I think that's it, guys. This is about the chapter. This is what I wanted to convey. Do a couple of problems, but still, without even doing problems on Van der factor, most of you have gotten the answers actually for the alpha questions or the Van der factor questions. Good. Okay. So I hope there are no doubts. If there are no doubts, we can go on with the next chapter. Right? Any questions, guys? Everybody understood the problems? Everybody understood what and all we have seen?
Understood.
Okay, cool. Right. So we are ready for the new chapter. So for the sake of being formal, I write the chapter. Electrochemistry. Right. So this is one of the most interesting chapters in chemistry. Like at least I like this chapter very much, right? Because there are a lot of not only chemistry involved, there are a little bit of physics also involved in this chapter, because obviously we are going to connect electricity with chemistry, and that's why the name electrochemistry, right? Like you will be seeing beautiful applications. Like basically like you will be knowing what exactly now we use batteries, isn't it? Like we use batteries in our mobile phones, we use batteries for our remotes, we use batteries in watches. Say when I go for electric vehicles, now that's what is coming through, isn't it? Like we are moving from petrol engine to the electric vehicles. So again, the applications in there, lithium ion batteries, all that, so on and so forth, the car batteries, anything, the chargers which you use for your mobile phones, for all these things, if you want to understand what exactly is happening here, the basics is what we're going to study about them, right? So once you are very thorough with the basics, now for any kind of device which gives you power, right? Any kind of device which gives you power, you will be able to actually understand what exactly is happening inside that particular thing. Right? For example, if I take a remote battery, I'll tell you what all are the chemicals present and what it's basically chemical reactions is going to happen. Right? In anything which gives you power, anything you call a battery or a power source, right? These are actually chemicals, and there are going to be some chemical reactions happening. Okay. Now, if you ask me, sir, is there any specific type of chemical reaction happening? Yes, there is there are two specific type of chemical reaction which will happen, and that is what is my oxidation and reduction. Right? So basically the chemical reactions are happening inside any battery, any cell, anything which is regarded as a power source, right? The chemicals which we use are basically going to undergo oxidation and reduction. Okay. Now, because I hope you all understand, I hope you all remember, how do you define oxidation in terms of electrons, in oxidation or reduction in terms of electrons? Can someone comment like how you will define oxidation and reduction in terms of electrons?
Oxidation is loss of electrons and reduction.
Okay, correct. So oxidation means the compound or the species has to lose electron, right? And reduction is opposite, gaining electron, right? So obviously now you will be able to understand how the electricity comes into the picture. Right. So there is going to be one substance which is going to get oxidized, and there is going to be one substance which is going to get reduced. In the sense, there will be loss of electron and gain of electron, and the gain of electron and loss of electron is going to happen because of the movement in electrons. There is going to be movement of electrons happening. right? And because of this movement, there is going to be current produced. Okay, now this is a very simple picture, right? Now we will look into each and every part, like in detail what we're going to see. Okay, right, fine. So first things first. Now, basically, so I told you that I'm going to have chemical reactions happening, basically oxidation and reduction reactions happening. Right now, let me tell you what is the difference between a normal chemical reaction and an electrochemical reaction. Right. So we know normal chemical reactions. Say I have two test tubes with me, two chemical compounds. I mix them both, and that's it. So basically, guys, and right. So what I was telling is, say I have A plus B giving C is a reaction. So what I understand is A and B need to be in contact. Is it not? I have to mix A and B, and I have to say supply some temperature, give some pressure, put some catalyst. Okay, so basically what I'm trying to tell you is A and B, I have to mix it, keep them in contact, right? Say use some catalyst or whatever it is to form the end product C. Okay, but if it is an electrochemical reaction, yes, I have say A plus B giving C, but this A and B are not going to be in contact. Okay, they are not going to be in contact. Without even them, they are very far away from each other, right? But still, I will be able to form the product. Okay, this is the main difference between a normal chemical reaction and an electrochemical reaction. Okay, right? And obviously here, if at all I have to use any energy consideration, say sometimes we call it as exothermic chemical reactions, endothermic chemical reactions. So obviously the energy involved here would be heat energy mostly, right? But here you see, along with the heat energy, it's not like heat energy will not be involved, but along with the heat energy, there will also be some electrical energy involved. Okay, so here it's only heat, right? And here it is heat as well as electrical energy, right? So that is the basic difference between a normal chemical reaction and an electrochemical reaction. And don't worry, we will see how are you going to conduct, how are you able to make sure that even though we don't have any contact, right, how are we going to make this reaction happen, right? So this is the overall picture, people. This is the overall picture. Now we'll try to understand what exactly is happening, what are all the components, what are all the what is the chemistry behind it, what is the physics behind it, right? We'll try to slowly understand. Okay, right. So first I wanted to understand the difference between what to say, a metallic, oh wait, or I'll talk like this. I will speak like, okay. So we know there are something called as conductors. Obviously, I'm talking about conductors of electricity. Okay. So when I say conductors, people, these conductors can be of two types, right? One are what are called as electronic conductors. The other one is what is called as electrolytic conductors. Okay, fine. So before we move on to see what are these electronic and electrolytic conductors, first tell me guys, for anything to be a conductor, right? For any substance to be a good conductor of electricity, what is the minimum requirement?
There should be free movement of electrons.
Okay, right. So yes, please tell me. Yeah, please go on.
So I just told it should have mobile.
Okay. So again, the electron, correct. So basically what you have to understand is, till now what you have studied, okay, till now what you have studied is, if something needs to be a conductor, I should have free electrons in there, right? Now that need not be always the case. Okay. Now if I have to give you a very general, say definition of conductors, for anything to be a conductor, I should tell you that there should be free charges present. It need not be always electrons. Okay, please understand that, right? What I'm telling you is, for anything to be a conductor, there should be charges in any form, for that matter, which should be able to move, and that is what we call it as free, right? And if these charge carriers or these charges moves, and yeah, that is how electricity is conducted. Okay. Now these electronic conductors which we see here are the normals we see. These are the metallic conductors where the electron is the charge carrier. that is the charge which you're talking about. Electron is the charge carrier. Okay, we're going to have free electrons present. But when I go to this electrolytic conductors, right now, okay, here you see, here I'm going to have the ions or electrons, both of them, right? I can even, basically ions are also charged particles, isn't it? I can have cation to be positively charged, anion to be negatively charged. Even these are charges, and if they move, and obviously that is also going to be a good conductor. Okay, right? So, and one more thing, what you'll be able to understand here is generally these are solids, right? Electronic conductors, your iron rods or your copper rods, aluminum wires, gold wires, all these things generally, right? You'll be seeing them in solid state, right? But here you will majority you will be seeing them in liquid state, majority. But I can have solids also. Solid electrolytes are there, right? But again, very like compared to liquid electrolytes, solid electrolytes are, the number is pretty less, but they are there. There is no doubt that they are not there, right? But so what you have to understand is electronic conductors, the majority charge carriers are electrons, and in electrolytic conductors, majority charge carriers are ions or electrons. And most of the electronic these things are solids, right? Electrolytic conductors, most of them are liquids, and some of them are solids. Okay, right. Now it's pretty simple, isn't it? Say now, if you want to understand what exactly is an electrolytic conductor, now say I have assumed that I have, say, NaCl solution. I have sodium chloride. Okay, now inside this I will have sodium plus, Cl minus and present. Say now what I do is to this I connect a wire, right? And I give it, say, a power supply. I should be doing it properly. Wait, I'll draw the diagram again. Right? Say this is my NaCl solution, right? I'm going to connect it to a battery. Okay, right? So obviously, like if at all you want to see any reading, say for example, you connect an ammeter here. Okay, there is an ammeter here. Assuming that my diagram is very bad, please bear with it. And assume that there is an ammeter. Okay, right. Now, on and only if this is conducting, right? If this liquid or whatever it is conducting, then only I'll be actually seeing the reading in the ammeter. Right, right. If this is not conducting, obviously circuit is not complete. So obviously, you are studying electrochemistry. You will be studying in physics. Which chapter is going on, guys? Electrostatics is over.
Yes, sir.
They have started current electricity.
Yes, sir.
Yes, sir.
Okay, then you must have some basic idea, or even in your 10th standard, you must have studied a little bit about electricity in physics. Anyways, right. So what you have to understand is only if this particular liquid or whatever it is conducting, right, I will have some amount of circuit completion, right? So what I see here, if it is NaCl, obviously there is going to be some reading in the ammeter. And why this happens is because I have the charged particles here, Na plus and Cl minus. Now you will see that one of the one of the things, right, is connected to the negative terminal of the battery. The other one connected to the positive terminal of the battery. So obviously you see the positive charge will move towards the negative side, and the negative charge, that is Cl minus, will move towards the positive side. Right. So this is exactly what is happening. Right. What do you mean by an electrolytic conductor, and how ions are responsible for conducting? This is just a small experiment which you can do. Okay. Right. Fine. So that is about electronic and the electrolytic conductors, a very basic thing. Now, next thing what you have to understand is there is something called as electrodes, right, and electrolytes. We just know. So what are electrolytes or electrolytic conductors? Okay, now please understand, people, these electrodes are nothing but they are electronic conductors, right? These are electronic conductors, and this we know are electrolytic conductors in the sense that here I'm going to have ions as the charge carriers, and in electrodes it is the electrons which are going to be the charge carriers. Okay, right. So now what you have to understand, people, when I am going to make them in contact, right, when I'm going to have an electronic conductor, and that electronic conductor is what is called as an electrode. Please understand, when I say electrode from now on, it is nothing but a piece of metal, right? Or in general, it is an electronic conductor. That's what you have to understand. Okay, so I have an electronic conductor, And if I keep it in contact with an electrolytic conductor, we'll see what happens. Okay, right. So what I'm going to do is say I have an electrolytic solution with me, which has ions, obviously. Say I will take zinc sulfate solution with me, aqueous solution. Okay, now what I'm going to do is in this, I am going to insert a zinc rod, right? So obviously you see this, whatever I have here, this is the electrolytic conductor, and this, whatever I have here, the zinc rod is going to be an electronic conductor. Okay, right, fine. So now what is going to happen? If I bring them in contact, if I keep them in contact, maybe you will not see them. If with your naked eyes, you will definitely not see whatever I'm going to tell you. But if at all you do some correct experiments, we will see what are those experiments. You will see that there's actually something happening. Okay, so what is happening if you ask me, right? So please understand, people, here inside the solution, I have zinc 2+ ions, right? There are so many number of zinc 2+ ions, so many, and obviously SO4 is present, no doubt about it, right? So zinc 2+ ions are there and Zn 2+ ions are there. Okay, and you see in the zinc rod, the zinc is in metallic form, right? The zinc is in metallic form. So what can happen is, you see there is a concentration gradient. What do you mean by concentration gradient? That is, in the solution side, in the electrolytic side, there are more number of ions, there is a more concentration of ions, but in the zinc rod or in the electronic conductor, there is going to be there's going to be basically no ion present. There is going to be no ion present. So what can happen? Two things can happen, people, right? Two things can happen. What are two things? Is now I can have zinc from this going into the solution as Zn2+. That is possible. Okay, or another possibility is the zinc 2+ from the solution can go here as zinc. There are two possibilities. Okay, and this is a natural phenomenon. We don't have to do anything, just keep them in contact. You will see that this definitely will happen. Some amount of, say, zinc will convert to Zn2+, or sometimes what happens is zinc 2+ will convert back to the zinc. This will definitely happen, right? So if at all you want me to give you some say the phenomenon wise, then I can give you this. There is something called as solution pressure. You don't have to remember this, people. Whatever I'm telling you now, this is just for extra information. And osmotic pressure. Osmotic pressure we already studied, but here it is a little different, right? So when I say solution pressure is from the electronic. If the ion go into the electrolytic, okay, electrolytic, please understand. Okay, from if the ions go from the electronic into the electrolytic, it's called, the phenomenon is what is called a solution pressure, right? And the opposite, when the ion moves from the electrolytic to the electronic, it's called osmotic pressure. But again, you don't have to worry about any of this. Do not remember the terms, do not remember the definition, no worries. But all you have to understand is, if I keep an electronic and an electrolytic conductor in contact, right, this movement of ions will happen. Okay, this movement of ions will happen. Please understand this. Okay, now let us see what is going to happen because of this. Okay, so I understood that. Yes, any doubts?
Sir, you said in the electrode there is no ions present, right?
Electrons, there is no ions present, but there is zinc present. Yes, please go on. Yeah.
Yes, sir. So, okay, sir. Okay, sir. So, ions and zinc are different, right?
Yeah. So basically, zinc in the metallic form can form zinc ion Zn2+, and zinc ion in the solution can go back to zinc. It's all about accepting and removing electrons. It's that simple. Yes.
Yes, sir. Understood, sir.
Okay. Right. Fine. So all you have to understand is, if I keep an electronic conductor and an electrolytic conductor of the similar kind in contact, there will always be this movement of ions, either from the solution or from the electrolyte to the electrode, or from the electrode to the electrolyte. This is what is going to happen. Okay. Now, because of this, what is going to happen? I will try to understand. Okay. Right. Say I have, again, I'm going to draw the same thing again, but a little better. Okay, Same thing. This is ZnSO4 and this is zinc rod. Now assume that there is going to be more amount of Zn2 plus produced, in the sense that there is going to be from the electrode there is more amount of Zn2 plus given into the solution. Assume that this only is happening. Okay, assume that this only is happening. Okay, now what is going to happen because of this? See, this zinc rod is neutral. There is no charges on this. Correct. Now, if this zinc rod is going to go into this as Zn2 plus, basically, can I say that this zinc rod is losing positive charges? Can I say that? Can someone tell me yes if they understood? Again, I repeat. I'm telling you that this zinc rod is what? Is neutral, right? And I'm telling you that the zinc from this is going into the solution as Zn2 plus. Or in other words, I can tell that this zinc rod is losing positive charges. Is that correct? Is everybody able to understand? Yes?
Could you repeat?
No? Yeah. See, what I'm telling is this is neutral, right? This zinc rod, whatever I have, is neutral. Right. Now I'm telling you that there is a natural tendency that from this zinc will go into the solution as zinc 2 plus. Right. What is happening basically from a neutral thing, I am removing positive charges. Basically, this zinc rod is losing positive charge. So what is going to happen? I can tell that there is going to be some amount of negative charges developed on the surface of the zinc rod. Yes, are you able to get this point, people?
Yes,
Right,
sir.
because of I have something neutral and that loses a positive charge, and obviously what will be the remaining thing? Remaining thing would be a negative charge, and that's exactly what is happening here. Okay, so if I just take this alone and zoom it, and if I zoom it, I will see that basically surrounding this I will have negative charges, right? But inside the solution, assume this is the solution, inside the solution you will have positive charge surrounding it. Again, the double layer of charge will be there. Okay, now this is understood, obviously, right? Because something overall everything is neutral, guys, right? Overall the electrolytic conductor and the electronic conductor is neutral, right? But once you bring them in contact, I told you there will be a natural phenomenon happening that from the zinc rod Zn2 plus ions are going to go into the solution, right? So the zinc rod being neutral is losing positive charge. So you see that there is development of negative charges, right? And the solution was initially neutral, right? Now what happened to the solution? What happened to the electrolyte? To the electrolyte, I'm adding more positive charge. So what happens? The zinc rod becomes negative and the ZnSO4 electrolyte becomes positive. Again, I repeat, zinc rod becomes negative because it is losing positive charge, and the electrolytic solution becomes more positive because it accepts more amount of positive charge. I want everybody to give me a yes in the chat box if they understood. Please go for it. I'm looking at the chat box now. Whatever we saw till now, I want everybody to give me a yes if they understood.
Understood.
Okay. Yes. Okay.
Yes, sir.
Right. Cool. So I hope everybody is with me. Right. Okay. Cool. Thank you so much. Right. So this we understood. Right. Now, guys. Now look at this. Now, obviously, there will be some kind of distance between them. Right. There will be some difference between. Sorry, not difference. There will be some distance which will be in between the positive charge and the negative charges. Correct. Now look at this. If you have already studied your electrostatics, say if I have say some Q1 minus Q1 and plus Q2, whatever it is, like obviously this will have its own potential, this will have its own potential, and if I take the difference between these two potentials is what is called as the potential difference. Correct, right? So that exactly what we are going to see here also. So excuse me. So I have an electrolyte and an electronic conductor kept in contact. So because of this movement of ions, I am going to have a potential created. Right? I am going to have potential created. Will I be able to measure this? Yes or no? Will I be able to measure this potential, people? Calculating is different. I'm asking you, can I measure the potential? Okay, let's put it in the chat box. Let it be a guess game. How many of you think, yes, sir, I'll be able to measure it? How many of you think that, no, I am not, I mean, we'll not be able to measure? Just put yes or no. Yes for,
Sir,
we can measure. Yeah.
Potential difference
Sorry.
between what?
So I'm not talking about potential difference. I'm talking about the potential which is getting developed because of the charges. Can I measure?
I think it can be measured, sir.
Okay, fine. So one answer is yes. Okay, so many answers for yes and one answer no. Okay, fine. So some of you have answered. Guys, please understand, right? There is a difference between potential and potential difference. Potential, we not only in this case, any case for that matter, we will not be able to measure the potential. All we can measure is potential difference. Please understand that. Okay. Now, if I have 2 points, like if I say that I have this Q1 and Q2, this will have its own potential. This will have its own potential, and that cannot be measured. What we can measure, if say this is V1 is the potential, V2 is the potential here, I will be able to measure this quantity. V2 minus V1, I'll be able to measure. Right? Hope you remember this. Okay. Potential cannot be measured, but potential difference alone can only be measured. Please understand. Please remember this. Okay, so what we developed here, because of the separation of charges, we understood that there's going to be so you can ask me here also. I have basically this potential, what to say, separation of charges. This negative will have some potential, positive will have some potential. Yes, I agree, right? There is some potential difference between this and this, but as one of the charts read, the distance between them is so small. Okay, so because of that, we cannot tell them as potential difference. I can take it as an overall something, and I can tell that this has some potential. That's all I can tell. Again, I repeat, you can tell me that there is separation of charges. There is negative charge, there is positive charge, and each of them will have its own potential, and I will be able to measure the potential difference. Yes, theoretically, very correct, right? But guys, the distance between these charge layers is very small. So I will be able to approximate them as a single entity, right? This is overall one system. That's it, right? So for this overall one system, since they are charged, they will have some potential. Okay, I think I have made my point very clear, right? Is there anyone who wants me to repeat, or is there anyone who wants to want to make a comment? Okay. So I suppose everything is clear. So again, the distance between them is very small. So I will not regard them as potential difference. I will just regard them as potential. There is some potential developed. So all you're trying to understand is when I have an electronic conductor in contact with an electrolytic conductor, there will be a potential developed. That is what is the story, right? And how the potential is developed, and that is what we have been seeing here, because there is a natural tendency of the electronic, the ions can move from the electronic conductor to the electrolytic conductor, or say from the electrolytic conductor to the electronic conductor. That will create some charge separations, and because of the charge separation, there comes your potential. Okay, right. Now you saw you saw ions coming from the electronic to the electrolytic conductor. Say if we take the same thing, right? If we take the opposite, say I have another solution with me, right? So which has, say this is copper sulfate solution, and say this is my copper rod. Okay, now in this case, now see, please understand, depending on the type of metal and the type of electrolyte used, from where to where the ions are going will be changing. Okay, last case I told you zinc, the ions were moving from the zinc rod to the zinc sulfate solution, right? In this case, what will you see is the copper 2+ ions which are there inside the solution will go into the rod as copper. Exact opposite process is going to happen, right? So what is going to, because what is going to happen, it is, I'm just going to have the charge separation to be ulta. So what is going to happen now? You see the copper rod is neutral. What I'm doing to the copper rod, I'm adding more amount of positive charge to the copper rod, correct? So what will happen to the rod, if you see, there will be formation of positive charges on the surface of the rod, and obviously the solution has lost positive charge, the electrolyte has lost positive charge. So surrounding this, I'm going to have negative charges. Very simple, very, very simple physics behind this. Okay, and same thing. Now again, since I have the same charges happening, and I'll be able to have some potential, have potential developed, right? And I'll not be able to measure it. Okay, now, so okay, theoretically what you're saying, I'm able to completely understand, but how will you prove it? What is the experiment? Like, how will I be able to prove that both these cases, that is ions moving from say the electronic to the electrolytic, or the ions moving from electrolytic to electronic, how will I prove that these potentials exist? Because I'll not be able to measure it, isn't it? Right? So for that, what we are going to do is I am going to connect this with this. Okay, I am going to connect this, like the zinc rod, that basically this entire system and this entire system, I am going to connect. Okay, if I connect, we'll see what happens. Okay, fine. I hope till now there are no doubts, people. If there is any doubt, please, you can ask. You're always welcome to ask any doubt for that matter. Okay, right. So let me connect them and see what happens. Okay, so I have please bear with my drawing, people. Okay, now you want to measure, you want to say we want the proof that the potentials are developing, isn't it? So what I do is I connect a voltmeter. Obviously, these are wires. These are normal wires. Whatever wires you want to use, you can use. And I have connected with the help of a voltmeter. Okay. Now, please understand, people. Here, I'll say, obviously we understood that the potentials are developing. No doubt about it. Say this is V1, and the potential developed here is V2. And this voltmeter now will measure the exact value. It will show the value to be equal to V2 minus V1. And that is what will be shown in the voltmeter. Right? So please understand, people, voltmeter or any other instrument can measure only the potential differences, but not the absolute potentials. We will not be able to do it. Okay, but with the help of some tweaking in mathematics, right, we'll see later, I will be actually able to give a value to this V1 and give a value to this V2. We will do it, right? But ideally speaking, we will not be able to measure the exact value of V1 and V2. All we can measure is the potential difference if I connect a voltmeter, and that value, the reading which will show, would be V2 minus V1. Okay, so if it shows any reading, right, I'm not passing any electricity, I'm not doing anything, guys, I'm not doing anything. This is just a setup. I have a liquid and I have a metal conductor, again a liquid with a metal conductor connected, not doing anything. You will see that there will be a reading shown in the voltmeter. This means what? Obviously the potentials are getting developed, and whatever I told you before is actually happening. Okay, now this is the basic principle behind all the things you're going to study after this. Okay, so if I keep an electronic and an electrolytic conductor in contact, there will always be some potential developed. There can be cases that there might not be any potential developed. Now that, if you want to see why, is here. Where is this? Yeah, so we talked about this solution pressure and osmotic pressure. These are actually, I can give you some values. Now, if this value and this osmotic pressure value are equal, that means what? Solution pressure, I told you, is the tendency of the ion moving from electronic to electrolytic, and osmotic is opposite. Right. So if these values are equal, that means what? Net, basically, the amount of ions going into the electrolyte and the amount of ions going out of the electrolyte is same. So that means what? Basically, there will not be any charge separation and there will not be any potential development. But if one of them is higher and one of them is lesser, definitely you will see that there will be some potential development. Okay, you don't have to go into the details, but you, like, if at all, sometimes you do the experiment and then sometimes you will see that there will not be any potential difference shown in the voltmeter. And what you have to understand is the solution pressure and the osmotic pressure are same. That's the main thing. Anyways, like, you don't have to go into the details. So I hope everybody understood how the potential is developed, right? and we are going to move on. Right. So we know there are something called as cells, right? Not your biological cells, right? We know we have cells, batteries, and all that, right? Can someone tell me what is the difference between a cell and a battery, guys?
The cells are
Battery is a group of cells.
Okay. A combination of cells is what we, well, then we get a battery. That's what basically I can have a series combination or parallel combination, doesn't matter. But if you have so many cells put together, right, that will form a battery. Cell is a single unit, single entity. Okay, fine. So in electrochemistry, people, the cells are divided into two types. Okay, basically cell is anything which has to do with electricity and chemical reaction. That's what you have to understand. Any cell for that matter will have something to do with electricity as well as something to do with chemical reactions. Okay, fine. So these cells in electrochemistry can be classified into two types. One are what are called as galvanic cells. The other one are what are called as electrolytic cells. Okay, galvanic cells and electrolytic cells. What is the time? Okay, we have 20 minutes. Okay, so now we'll see what is the basic difference between these two cells. Okay, now please understand, people, for galvanic cells, see, in both, as I told you, in any cell, in galvanic cell or electrolytic cell, the chemical reaction is going to happen is an oxidation and reduction. Both of them will happen. Both in both galvanic cells and electrolytic cell, oxidation will be there, reduction will be there. There will be a cathode, there will be an anode, there will be everything will be common, except for the thing which I'm going to tell you now. What is the difference? Now, the difference here is in galvanic cell, the chemical reaction which we take is a spontaneous chemical reaction, right? In a galvanic cell, the chemical reaction we take is a spontaneous chemical reaction. Okay, now the question is, what is a spontaneous chemical reaction? Second question is, thermodynamically, let's say thermodynamically, how will you define a spontaneous chemical reaction? Go for it. First question. Okay, we'll answer the first question first. What is a spontaneous reaction? Okay, what do you mean by any spontaneous process? What do you mean by that?
So fast, sir. No external.
Okay, no external what?
No external support is required.
Okay, that's the best way to put it. Yes, any other answers? I think someone else was trying some answers. Yes, please. Okay, fine. So basic, yeah.
Exothermic, endothermic also occurs. That is, energy is getting released.
Good. Yes, these are all the things. Okay. So yes, all the mentioned points were correct. So in a spontaneous reaction, or when I say anything happening spontaneously, means what? I don't have to do anything for that particular process to occur. The process or the reaction will happen on its own. For example, say if there's a slope. Okay, I hope you're seeing my video. Don't look at the screen. Like you have a slope. Okay, so now I put a drop of water here. I just put a drop of water. What will happen? The drop will eventually fall down. Am I doing anything there? I'm not doing anything. The water droplet will eventually fall down because there's a slope. And that is how nature works, right? Say another spontaneous reaction is like, say, sun rising in the east. But again, technically speaking, there are differences, but still, right? Sun rising in the east, again, it's a spontaneous reaction. We are not doing anything for the process to happen. Or say, I have a hotter body. I have a colder body. I keep them in contact. What will happen? The heat from the hotter body will go into the colder body. Again, a spontaneous process. I'm not doing anything. I'm just keeping them in contact, right? So anything, any reaction or any process which doesn't require any external support, we don't have to do anything for those reactions or processes. They will happen on their own, right? Like say, for example, if I have to speak chemically, say I have a sodium, little amount of sodium, I put in water. You must have done this experiment in 10th class. You would have seen how violent the reaction is, isn't it? Na plus H2O will give NaOH plus H2. Spontaneously, so much amount of hydrogen will be avoided. I am not doing anything. I am not supplying any heat. I am not supplying any catalyst. I am not doing anything. I am just putting them in contact. Okay. Now, those kind of reactions are what are called as spontaneous chemical reaction. Okay. Now, please understand, since we are not supplying any energy, Okay, since we are not supplying any energy, right? Now, all spontaneous chemical reactions are exothermic reactions. Please remember this. Since we are not supplying energy, obviously the reactions or the process will give us energy. That is how it is. Okay, since we are not supplying or any external energy, the reaction or the process will give us energy. So that's why we say that all spontaneous processes are exothermic in nature. Okay. Now, thermodynamically, how will you define a spontaneous process? Any idea? There is one quantity, right? Ah,
Release.
yes.
The reaction
Sorry.
where energy is released. Reaction where energy is released.
Okay. There is one specific term, one quantity by
Transfer
which
of
will
heat.
transfer of heat. No, I am just expecting one quantity, a thermodynamic quantity, which defines a spontaneous process.
Enthalpy and entropy.
No. Before the someone else, what is it?
Gives free energy.
Gives free energy. Okay, correct. Enthalpy, entropy. Yes, Kanna, what you're telling is correct. Enthalpy for an exothermic reaction can be, say, we can tell entropy, we can tell. Now, all these things, enthalpy and entropy are the things which combines together to give one quantity, and that is what is called as your Gibbs free energy. Can you tell me the equation? Anybody can tell me the equation connecting Gibbs free energy, enthalpy, and entropy? What is the equation, guys?
It's delta G is equal to
Ah.
delta H minus
Ah.
delta S.
Absolutely correct. So I have delta G is equal to delta H minus T delta S, right? So obviously we can speak in terms of this, or overall I can speak always in terms of this, right? So one point came from some girl saying that delta H and delta T. Yes, absolutely correct. With the help of that also I'll be able to so define a spontaneous reaction, but a more, say, generic method, like, or say more convenient method would be to talk in terms of delta G. Okay, so with the help of delta G or Gibbs free energy, how can you tell whether a reaction is spontaneous or not? By looking at the value. How should be the value of delta G so that that process is spontaneous? How should be the value?
Less than 0, sir.
Correct. So for a spontaneous reaction, delta G will always be less than 0. Remember, negative value. Okay, the delta G, the Gibbs free, the change in Gibbs free energy for a spontaneous reaction or a spontaneous process will always be less than 0, a negative value, right? So for any process, right, if you see that the delta G value is less than 0, that process is, or that reaction is spontaneous. Okay, so why did we start all this? I told you this because in galvanic cells, we are going to take always only spontaneous reactions. On always for spontaneous reactions, delta G will be less than 0. Okay, fine. So what are we going to do with the spontaneous reactions? Right now, please understand, people, we are trying to connect chemistry with electricity. Correct. So what you're trying to do in case of a galvanic cell is, I told you that delta G will be less than 0 and the reaction would be exothermic. So what I'm trying to do is, I am trying to, obviously you see that the reaction is giving me energy, isn't it? The reaction is giving me energy. So that energy, I call it as chemical energy. Right. Now this chemical energy is given to me by the reaction. Okay, now what I'm going to do is I am going to convert this chemical energy into electrical energy. And that's exactly what we are going to do in a galvanic cell. Okay, so again, I repeat all the points in a crisp manner. Galvanic cell uses spontaneous reactions, and spontaneous reactions are going to give me energy because they're exothermic and delta G is less than 0. And I'm going to use that chemical energy given to me by the chemical reaction to produce electricity. It's like simple energy transformation. Energy can neither be created nor be destroyed, but can be transformed from one form to another form. Here it is transformed from chemical energy form into electrical energy form. So basically, wherever you see you are giving power supply, when you go to your physics labs, right? You will have a battery source giving power supply to resistors, isn't it? Now that is actually a galvanic cell, right? Now one specific example is what is called as your Daniel cell, which is what you have been using in your physics labs to giving power supply. And whatever I told you now, that's exactly is what is happening in a galvanic or a Daniel. Daniel cell is a specific example of a galvanic cell. Galvanic cell is a whole. Daniel cell is an example which you use in your physics labs to give power supply, right? So anything which gives you power supply, anything which gives you electricity, right? All those comes under galvanic cells. So basically your car batteries, your whatever the remote batteries, whatever, wherever you see something giving you power supply, all of them are galvanic cells. Okay. Now we'll try to understand what exactly is the chemistry behind it and how are we going to correlate to delta G and all. We'll see next class. Now we'll concentrate on what do you mean by these electrolytic cells, right? Now it is exactly opposite of galvanic cells. Here I am going to make, right? Here I'm going to make a non-spontaneous chemical. Obviously, I'm going to take a non-spontaneous chemical reaction. And obviously, a non-spontaneous chemical reaction energy has to be supplied, isn't it? Right? I have to make sure that I have to supply energy for the reaction to happen, right? And that energy supplied, right? The energy supplied, sometimes we do it in the form of heat. Sometimes you must have seen reactions where light is used as energy. Now, in the electrolytic cells, electrical energy is what is supplied, right? Electrical energy is what is supplied to the non-spontaneous chemical reaction. Now the non-spontaneous chemical reaction will occur. That means what? This is exactly opposite of what we saw. Electrical energy is converted into chemical energy because we are going to take a non-spontaneous chemical reaction, and in a non-spontaneous chemical reaction, we have to supply energy, and that energy supplied is nothing but electrical energy.
Sir?
Okay. Yeah.
So in other words, electrolytic reaction is actually an endothermic reaction.
Absolutely. All not you should not say electrolytic reaction. These are electrolytic cells, right? In electrolytic cells, I use a non-spontaneous reaction, and obviously it is endothermic. All non-spontaneous reactions are endothermic. Yes, correct.
Okay.
Okay, right. So what is the time? Yeah, we still have time, right? So now maybe I'll give you an example, right? For example, guys, right? Say I have NaCl giving sodium and chlorine. I write the opposite reaction. Na plus Cl2 giving NaCl. Say this is reaction number 1. This is reaction number 2. Now, based on your experience, right? Tell me whether which one is spontaneous, which one is not spontaneous. Right? Say you should tell 1 is something, 2 is dash dash, whatever it is. Which is spontaneous, which is not spontaneous.
First is non-spontaneous.
Good, right? First is not spontaneous, and second one is spontaneous, right? Second one is spontaneous. This is not spontaneous. Now it's very easy, right? Obviously, I know sodium is very highly reactive. Chlorine is also very highly reactive. So when I bring them in contact, I will easily form NaCl, right? But the opposite reaction obviously will be a non-spontaneous chemical reaction. So what I'm trying to understand, or what I'm trying to tell you, is if at all you have sodium chloride and you want to extract sodium and chlorine from NaCl, you have to supply electricity, right? You have to supply electricity. Now, from the name itself, we can understand electrolysis, right? This process is what is called as electrolysis or electrolytic cells. Lysis means what? Lysis means separating, right? Electro obviously means electricity. Okay, so with the help of electricity, I am going for separation of the compound into its constituent elements, and that's what we do in case of an electrolytic cell, right? And obviously now this is not the exact reaction we can use. In case of a galvanic cell, we will use some other reaction, but obviously that reaction will be spontaneous. Don't worry about it. Okay, right? Any questions, people? Any questions till now? Right? We saw how a potential is developed, right? How do we measure the potential difference? Then we went on to see what are the different types of cells. Galvanic cells, what are galvanic cells? Electrolytic cells, what are they? What is the basic difference between them? What energy is converted to what energy? All these things you have to remember. It's all pretty logical. There's nothing to mug up here, right? It's all purely logical, right? And I will give you more sense. I'll give you more insight in the next class. Okay. So maybe first we'll take galvanic cells, we'll finish them, and then we'll go for electrolytic cells. Right. Any questions, people?
No doubt, sir.
Okay. So what is the time? Yeah, almost we have 5 minutes. We can actually wind up the class because I cannot take galvanic cells now. It will take some time for me to complete. There will be some discontinuity, right? So if there are no doubts, people, we can wind up the class, right? Is it okay? Right. So let me,
Yes, sir.
yeah, let me stop sharing my screen. Yeah.
Sir,
Okay.
can you give me
So, okay.
your phone number?
Yeah, sure. My number is 8939.
One second.
And whomever don't have, you can take it down. You can always contact me, guys. Whomever doesn't have my number. Yeah. So
Can you
my
repeat
number is 8939 21 9916.
Okay, sir. Thank you, sir.
Right? 8939 21 9916 is my number.
Okay, sir.
Okay.
Thank you.
Fine. Okay, guys. Thank you so much. It was a very nice class. We'll again meet. I think Sunday the other sir will take. So we'll be meeting on next Sunday after this. Okay. Fine. Thank you so much, people.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Sir.
Yes, sir.